I wonder if you can.
What were you doing?
You're showing to. Right? Yeah, I think you can even do it a little.
Oh, nice.
I just like that even more.
You're not even in the front row.
Even, I don't know if you will be watching these recordings for lecture content, but maybe you will watch it for just see yourself. Or we can wrap it up and issue as TV show. So why don't you grade yourself?
Okay.
So since I do not know how comfortable you are in disclosing identity, I put little numbers and I have a dictionary, so you will not see. I have hidden the names with little stickers, and I can keep doing it in the future. If you're sensitive, if you all will tell me that you don't care, we can do it open. So I will distribute the homeworks and show the keys as we will grade it together. And probably you should get also extra credit for doing extra work, right?
Sure.
Oh, you already got some.
I got.
You can do.
I can do two.
Then you will get double credit.
Oh, I'll do it.
Okay, yeah, I have two.
While you're typing.
Yeah, one hand. Okay.
Yep. Do you have colorful pens to write? Who needs the next pen? This one to be brighter.
Okay.
Alyssa, you have something to write with?
Yes, I'll take a private.
I'm not sure if I can throw it to the target with a good precision.
What?
Check it out.
Wow.
There's equations.
Oh,
You were gonna test
that's great.
it.
So, we'll get to it maybe on Monday to cover. And Steven needs to decide which subject. So you can send me an email if you plan on a specific subject. Okay, so here are the points. So, right? So try to be generous and give as much points as possible. So withdraw points if stuff is completely missed.
Oh, it's gonna be 0.
Extra credit, 20 points. Good.
Okay.
Okay, so
Okay.
you already. Okay, probably you need to put camera on the tech support. Can you please focus on right now here? Focus camera on instructor. Steven, do you see the class or the whiteboard?
I see what is projected on the screen currently.
Okay, good. Let's keep it this way, and I'll ask to swap on screen. So this little image is what we did on the MATLAB, right? And it is the answer. By the way, you can grade not without listening to me, right? Since you all know what is the answer, I will be just slowly going through. So we need to reproduce the shape of this function by Fourier series. So for zeroth term, it is not a harmonic, it is harmonic with zero frequency, so it's just average over the duration of a period, so just 1 over L to have it normalized, and then integral of the function. And then since we bring them to two pieces, it will be 0 in one and 1/2 in another, so it will be 1/2, right? From 0 to half of the period, 1 over L times L over 2, 1/2. So, and here are some guides. If there is no final answer, which we on the next, if there is a final answer and it is correct, then just give full credit and jump to the next stuff. If something is screwed up, then try to assign here and there a little points. So if it is split on two integrals, extra points. If it is the first answer is correct, extra point. Then for cosines, one may try to integrate and observe that no matter what will be the integer number here, the cosine will be always even function, and our the function here, which we consider, is odd. So any cosines will be 0. So if the person whom you are grading tells that all A terms which are expansion coefficients of cosines are zeros, extra points. I don't know, I wasn't counting. Maybe if you assign extra points, it will be more than total. And then for the coefficients in front of sine, it's also splitting onto two parts, right? You need only integrate from 0 to L over 2, and then integral of sine is what? Minus cosine, and then you plug in definite values when x equals L over 2, then the argument of cosine will be pi. And since you are performing integration and exchange of variables, you redefine relation between your x variable and y variables through L over 2 pi, right? The answer of the E1 index will be 1 over pi. At least it was when I was doing it. So try to be generous. If it is positive and non-zero, just keep the point. If it is something way off, give less points. And then when you go further up to different values of indices, if they are even, they will be zeros. If they will be odd, there will be one over n pi. So either this answer or better, this answer is final one. So if one plugs in the expansion coefficients and puts, so there will be no cosines, only the sines. So the first term is 0, second, the zeroth term is 0, first terms in front of sines E1, third term E3, and the rest of terms are zeros. So the summation together of this sine and cosine with certain frequencies adding together will give this step function. Problem number 2. if Hamiltonian is 30 points, if wave function is 30 points, if energy has momentum square over 2m in terms of this wave vector points. For number 3, let's go to the sum of if there is the right answer. And I'm making mistakes in this factor sigma over 2 myself all the time. So if the factor is here 2, 1, or 4, just close your eyes. If something is similar to this answer, just give it credit. If someone doesn't give full answer, then let's go through the steps. So the stuff that we are doing is integration of over x of in front of x square is 1 over sigma, in front of x is ik, and if 15 points, if there is an attempt to identify full square. Oh, if there is a correct answer, just give full credit. That's it. If there is an attempt, even not completely successful, give partial. So if the full square is identified successfully, and if there is a reasonable mu are able with additional credit. If the one whom you are grading is able to identify this integral with square root of pi equal. Okay. I think you're done, right? And I'm asking you for little favor. Can you add together all points and write them in a circle on the top?
Were you serious about giving 20 points to 0 question or not?
So everything except 0 counts to 100.
Okay.
And extra points helps as a safety caution. So like 100% A. 120 is kind of doesn't, it will be still A, but if something else is missed. You have good records in your grades. And I will see anyway if some parts of the something was unclear as a feedback for me to present it better.
I think the question that I struggled with the most was question 1. I didn't know what the
And
question
it was add together all grades and together. Oh, okay. Yes.
For question 1, on homework, it was really hard to figure out what the actual question was. If that makes sense. So I think if like there's text here, I think that like it could be phrased differently. So like I didn't understand how to even start, I guess, is my problem. So I spent a lot of time staring at it, trying to figure out where to go.
Send an email where it makes sense.
Okay, yeah, I just since I had problems, I couldn't start until Sunday.
Until you spent like 10 hours.
Yeah.
Oh, thank you for the feedback. Where's the final total?
Oh, no, that's not.
Okay, good. Okay. Cool.
And all.
Answer.
This is the first homework.
Oh, okay.
I gave you everything.
You're tough, really.
No, I'm not. You can give her more points. I would love it if you could.
Oh, you're really nice. So my trick
I would
is
love
this.
that too. And that is who it is.
Next time I will try to pair so that there will be a possibility of revenge.
All right.
Give her 100. I did what I could.
Okay. So now actual lecture. I think we have a little time after this fun session. So who we are and what are we doing? Oh, it's a lucky number and it's Friday. So we are predicting the future of an electron that has wave nature. And generally it should feel attractive force of some ions, positive ions, but now it is not because we want some simple problem. So we have three electrons in one-dimensional space. We did practice third way of predicting future, which is expansion of Schrödinger eigenstates of Schrödinger equation and matching the initial condition. And this approach did help us to recognize that width of initial Gaussian wave packet of the electron will expand, right? The second question is, we hypothesize that center of the wave packet will either move with constant velocity or stay still. In our solution, it stays still because we did not give it initial momentum. And we can repeat the same exercise we did with non-zero initial momentum, but it will be a little more exercise that maybe we are not looking forward. And there is a way to get through this question quicker. So we'll waste, so to say, some time on new approach, new tool, new method, and then we'll address the question of the movement of the center of the wave packet in like 2 hours. So I'm going to show the expected outcome. So if you were sleeping, which I doubt was weak, that's not fun. Now it's time to wake up and concentrate. The rest, if you saw this equation before, you have an idea what it is, you do not need to see the rest. I'm going to summarize it in 5 minutes, and then the rest will be just explaining where it comes from and how to use it. So we do need to set a bridge from this abstract theories to real life, to outcomes of measurements. And the outcomes of measurements are always observables, some expectation values. And we already know how to do it in Schrödinger approach. We find wave functions, construct them with operator of an observable, and get the prediction of results of the experiment. But it looks like a big waste of resources to compute wave function all the time. It has so many information in it that without computers and for some complicated problems where one cannot solve with pen and paper, it becomes not cost efficient. If you need just one number or one function, or this number is function of time, is it possible to do the same way as people were doing in classical theories, classical mechanics or physics? Just write an equation for the variable that we need to find without any wave function. Is it possible to do similar thing based on quantum works? So this bra and cat symbols do stand for expectation value of some A means arbitrary. Time dependence means we want to learn how it changes in time. And we will come to there is an equation that allows to predict trajectory of an observable, to predict future of a measure without knowing wave function. So if you do know the operator that we want to convert into observable, and if you know Hamiltonian, then it is possible. So we bring this aha question. Okay. There is a thing that this dangerous comma. This comma is not just a comma, it has a hidden meaning in it. And it means we'll go over it, but this comma means that one needs to expand this whatever is in brackets in the left and right comma into two terms. Product of these two things in proposed order, and then minus same two things in the inverse order. So if it will be numbers like 1 and 2, 1 times 2 minus 2 times 1 will be 0. Makes no sense. But since quantum operators often do not compute, as you saw for this example, x and ddx, it could be reasonable. What else? These brackets means procedure of finding expectation value. But this procedure can be thought of without without any knowledge about exact shape of the wave function. So we can process this equation as so-called operator algebra. And then, if you do everything carefully, this equation will set into linear differential equation that one can solve. Linear differential equation only for observable that is interesting to us, and it will be much cheaper than a equation or less equation. And the name of this force wave in the future would be Heisenberg equation of motion. So they were like friends and competitors trying to design quantum theory from the examples. Okay, so now let's start. Probably second last year I was delivering this lecture from online. There were always so much text. So when we met last time, not for the lab, but in class, what were we doing? Hermitian conjugation. Yes, we found that Hamiltonian itself is Hermitian, so we can transpose it, conjugate, and nothing will happen. And we were also enjoying boxes that I was told. Right? Square boxes, rectangular boxes, a different thing. So those boxes and property of Hermitian property of Hamiltonian will be a step, a building block, cornerstone for this forced wave product diffusion. And I think this text is just summary of what we did last time. So we pretend that we believe in Schrödinger equation. And we believe in the protocol, in the equation to convert wave function into expectation value, right? So this protocol uses wave function and wave function conjugate, right? And now we do want to be a little abstract. It's a famous, it's not very ridiculous, but it is famous joke as preschooler is assigned to make arithmetic tasks. Assume you got 2 apples and then another apple. What's it? You didn't give me apples. I will not do it. So it is a standard human approach to quantum theory as well. So like, if we do not have wave function, why should we do something? on one hand. On the other hand, we are trying to be a little above this level and to think in abstract way. Assuming that we have a function, what can we do? So the wave function that we use in the protocol to predict outcome of experiment is wave function itself and when wave function conjugated, psi star. Okay. And the boxes that we were doing last time for this operators acting on the wave function and conjugated wave functions are different. For regular wave function, operators act from left to right. From conjugated, it acts from right to left. So we will use this program, and you already know the answer. So our goal is to get differential equation for expectation value, which will work even if you do not know the wave function. So these two equations were main outcome of our last meeting. Maybe we did formulate them a little bit in a different way. So our favorite Schrödinger equation and our least favorite Schrödinger equation for conjugated wave function. So what is different? Sign different type. A little observation. So when we have our typical time evolution operator, first we predict the future, we have a minus sign here. So times goes forward, multiplied by minus. If we swap, so the E minus here jumps into evolution operator. Right? If we integrate the Schrödinger equation. Or we did backwards. If you differentiate evolution operator, we are getting Schrödinger equation. They are interconnected. This minus I over H bar is the same minus I over H bar. So if you do conjugation and get plan plus sign, our evolution operator for conjugated wave function will have plus I over H bar. And if we keep thinking in the old-fashioned style, we can think that it is still E minus I over H bar, H, but then instead of time we have negative time. So conjugated wave function is a little time machine. We are propagating backwards in time. Do not think about it. We do not have time machines in real experiments, but mathematically it's propagation backwards in time. At least it can be thought this way. Or if, remember, I've already forgotten this word you taught me, spool. So in the spool that we were doing on the lab, the thread is threaded right hand. And if you go in time backwards, or if you do conjugation of wave function, it will be unthreaded backwards. So going in the opposite direction. So we do have two Schrödinger equations for two types of wave function. And now we need to utilize it. And at one point we need to get rid of wave function and just get equation of motion for the observer. So the top line is our favorite prescription. A bridge from abstract theories to real world, which has typical wave function and conjugated wave function. Let's do a mathematical experiment. Let's just take the derivative of this stuff and check what happens. I would prefer to write it over, but since slides are here, let's use them. So it is everything that we know from calculus. Derivative, integral, and then product of three functions. Interestingly, the integration goes over one variable and differentiation goes over another variable. And long time ago, we did agree that our function is so good that one can separate its variables, space and time, so they're independent. And if variables are separable, then one can swap the integration and differentiation. So they are linear operators, they apply different variables, they compute, and they can be swapped without any penalty. We need to use this benefit because we do know how to differentiate product of functions. Okay? Everything is set up. Everything is made for humans to make life of humans easier, not to torture their minds at the poached time. And now, one applies product rule. Right? So derivative of a product is product of a first function times the rest unchanged, plus derivative of the second function, and first and last are unchanged, plus derivative of the last one, and first and second are unchanged. Make sense? And generally, this middle term should be there, and it is needed if you want to become professional scientist. Win a federal grant for like at least $1.5 million, and buy equipment for femtosecond chemistry, or get resources at X-ray, attosecond facilities. When things are changing really quick and operators change in time. This is possible, and this is also an interesting scientific area, but in majority, I wouldn't say a vast majority, but like 90 or 95% of the tasks that one needs to look at, the operators are time independent. And for this class, it will be very reasonable to accept the time derivative of operator is 0. Generally, there is not, but it will be okay just for me. Then we will have only first and last term. So what do you see? I'm so upset that I have typed in the past because I like writing over. Do you see, again, remember this modern cell phones make you photo collection by if you take photos from the cell phone, by the end of the year it gives, I have a new collection. Here are all photos with the person named this way. Here are, so there is a face recognition. Do you recognize any old friends in this write-up? Anything that... Huh? Yes, but even more advanced. That's... Huh? Yes, it's one old friend that used for normalization and finding expectation value, but I already have a little hint by the under brace and words plugged in. Let's look here. So we do have equation for time derivative of wave function, and we do have equation for time derivative of the conjugated wave, right? So here is one first old friend, here is our second old friend, right? So we can just plug in, instead of time derivative, we can put this Hamiltonian, whatever. And then there will be nothing about time on the right part. So we just plug in the right part of Schrödinger equation for this forward evolution, and right part of the Schrödinger equation for backwards. So when we will swap slides to the next line, highly likely, instead of this dt, there will be minus I over h bar h psi. Here will be plus I over h bar psi star h. Okay. Yes, it is. Now let's analyze what we have. So this part comes from Schrödinger equation, and we can just send the factor to the front. Okay. Both terms did came with plus signs because we just regularly applied the derivative of a product. Right? And now we put forward the factors. So for evolution forward, the factor is minus I over h bar. For evolution backwards in time, the factor is plus I over h bar. And this difference of forwards and backwards evolution in time gives the final answer. So a little bit more. If you look on this expression, here it is ach, here is ha, right? They swapped in the order. Or just type ach, ha, minus ha. What else can we see? One can move common factors out of brackets, right? If some factor is repeated in each term, we can put it out of brackets and simplify. It was our, well, there were no favorite exercises in high school, but we did it. So, other common factors. So, psi at the end, here and there, it's a common factor. We can put psi star in the first and second term, we can also put it outside. And this I over h bar can be put very outside because it is constant, it will not be affected by integration. So we have integration, we have psi star, we have psi, and here inside the brackets we have only subtraction of the products of operators. Hamiltonian, which is operator of total energy, and operator of the stuff that we need to know. But they are in the different order. If they would be in the same order, it would be 0. And it will be strange. It will mean that observations, results of observation will not change in time. Same, no matter what. Just not right. But here we do see that result of observation, its change of time of the result of observation depends on mutual relations of the operator for the observation and Hamiltonian. So your first suggestion about the recognizing a friend old friend in this mathematical sense, was psi times psi star. Can we look at this expression here as a procedure to find an expectation value of some new operator V? Can we? Why not? So we have integration, conjugated wave function, regular wave function, and everything what is inside is a new operator. Okay. Oh. So, because every person inside is lazy, one wants a shortcut notation. So instead of repeating 1, 2, 3, 4, 5 symbols, one still writes 5 symbols, but they take less space. 1, 2, 3, 4, 5. So brackets means commutation. If one swaps 3 together. Basically, we are done for today's meeting. I hope there will be no slides after. Right now, it looks a little boring and abstract and unpractical. And we do have an equation which you can brag that you are experts in Heisenberg equation of motion, which will sound impressive to your colleagues. But we didn't solve it. So once we solved Schrödinger equation for this expanding wave function, now we need to solve this one. When we will try to plug in realistic operators, something that you may observe, this commutation rules will simplify stuff that is placed there. So it will be some new operator, B or whatever. And then it will be differential equation between expectation values of some observables. And typically, it is not a single equation. Here will be some new operator B. Then you need to write another DDT with B equals R H B. And often when you write down an equation for this B operator, this equation will result in operator A. And then it will be a system of two differential equations. Like time evolution of it's not operator anymore, it's expectation value. Operator A will depend on some function of expectation value for B, and differential equation for B will depend on A. And then it will be a set of couple of differential equations that is somewhat easier to solve compared to finding Schrödinger equation solution wave functions. So the couple of differential equations is part of regular differential equation class, and equations like Schrödinger equation, when one is getting function of more than one variable, it's not part of basic differential equations. It's differential equations and partial derivatives, and it is considered as a little upscale version of D. Therefore, it's a little challenging to solve. This will be easy. Oh, okay, I lied. One more step. If through operator algebra one observes that commutator is 0, it means results of measuring this operator will not change over time. So if you measure it again, again, and again, and you will get the same. Time derivative equals 0, it's a sign that operator can use with semicolon. And other, its logic goes both ways. If it commutes, time derivative will be 0. If time derivative is 0, it's a signature that operator commutes with semicolon. And our examples of commuting operators were like momentum and momentum squared. You commute, they can be measured simultaneously. Thank you for the patience. Have a nice weekend. Thank you. And you bring some homeworks on Monday. No one objects. It's reasonable. Send me an email. I'll be happy to answer.
Come back?
Huh?
Do you come back?
If one wants more pens, please.
Thank you.